Hello, my name is Prashant Shenoy, and I am a professor in the College of Information and Computer Science at the University of Massachusetts. In this talk, I'm going to describe some of our ongoing research on smart cities and specifically sustainable smart cities. So let me start with some motivation for our research. As we all know, the Internet of Things have now become commonplace, and there are sensors and actuators that you can now embed everywhere in the physical environment at low cost. There are already more than 25 billion such devices that have been deployed in recent years, and that number is expected to grow dramatically in the coming years. This has been a result of the miniaturization of technology and the ability to embed ubiquitous wireless connectivity into devices and into sensors in the physical infrastructure. The rise of IoT has led to the emergence of several new application domains that are broadly related to smart and connected cities. These range from smart health as a result of availability of wearable devices, smart buildings and smart homes, smart transportation, uh, precision agriculture, smart manufacturing, and so on. Now, our work views these domains as data-driven cyber-physical systems. Now, cyber-physical systems are systems that link the physical world to the cyber world. And this is done through the integration of computing and networking that allows us to monitor, analyze, and control physical processes. Now, an example of such a cyber physical system is the heating and cooling system that you might have in a home or a building, which is often controlled by a smart thermostat. In this case, it's Google's Nest thermostat that can be controlled to the cloud. That also controls your physical infrastructure, which is the air conditioner or the heating system. Now, both this cyber and physical systems also are coupled with humans that live in the environment and are impacted by the heating and cooling system through comfort that it provides. Now, our work specifically looks at data-driven systems, which can be characterized by sense, analyze, and response systems that are shown in this figure on the right here, where you take data from sensors, you analyze it through various means, including, as we will see, machine learning techniques, and then you can provide feedback to users or actuate your sensors. And cyber physical systems are increasingly using this data-driven sense, analyze, respond architecture. And there are two examples shown in this figure. One is smart transportation or fleet management, where there are sensors that are deployed onto vehicles that have cellular connectivity. They send their sensor data to the clouds, where it's subjected to analytics. And then you can give feedback to drivers saying it's time to take a break. You may be getting tired from a long drive, or more intelligent optimization such as scheduling services and so on. The other example here is a smart electric grid, where you have flexible loads or meters that actually can monitor the electricity usage of these loads, that communicate with a smart electric grid and have ability to control these loads through techniques that are referred to as demand response and so on. Now, our research looks at these problems of data-driven cyber-physical system through different lenses. The first one is looking at it from a systems perspective, and the other is looking at it from the AI perspective. And in reality, you have to actually look at it from both perspectives. So what you need is a symbiotic approach that addresses these problems both from a systems and from an AI perspective. Now, what I'll do now is describe some of our ongoing research efforts that look at data-driven cyber-physical systems from both an AI and a systems perspective. And in particular, I'm going to focus on the energy domain and talk about sustainable smart communities. Now here we have communities, there could be cities or they could be villages that want to live sustainably. And by that we mean that they need to consume natural resources such as energy, water, food in a sustainable manner. Now, one way to do this is to make the community net zero or even zero carbon, which means that the amount of energy or carbon it consumes is neutral in some fashion. And there are many technological innovations that have emerged in recent years that are going to allow us to design net zero energy communities in the future. And these range from renewable energy such as solar and wind and energy storage such as batteries, electric vehicles, as well as buildings that are themselves intelligent and net zero in some fashion. So I'm going to now describe some work that we have been undertaking in our research lab that addresses some of these issues. So I'll describe four specific projects, which are nuggets that provide some glimpse into how we are approaching these problems, both from an AI perspective as we will see from a systems perspective. So the first project is called Solar Click that is shown on the left on this slide. And what Solar Click is designed for is a problem called anomaly detection. So here we have solar arrays that have been deployed. They may be there on rooftops of homes or buildings, and often they might have developed some sort of electric fault, or the array may be covered with dust or snow, and it may be producing less than its optimal capability. Now we want to detect when such problems occur and alert either the homeowner or the operator saying there is a problem, you need to come and fix it. So what we have done is we have developed a technique that we refer to as sensorless anomaly detection. Whereas the traditional approach for trying to figure out if there is a fault is to actually deploy sensors on these arrays, which can monitor the production. And if you see a production loss, you can send an alert. But often these arrays don't have any sensors deployed on them. So our technique actually does not require any sensors. Rather, it uses a machine learning technique that looks at a peer group of arrays, which are solar arrays that may be nearby in that community or in that city, and it uses the production data from those peer groups to predict what could be the production of the solar array. And the idea here is the weather in a region is going to be similar. It may be sunny or it may be cloudy, and the entire region might see that a similar weather pattern. So solar arrays that are deployed maybe in a neighborhood or in a small town or in a region will have similar generation. And we exploit these correlations to design a model that allows us to predict the generation of this array. And if the observed generation deviates from the predicted generation, you know that there is a problem. And we can deal with issues such as transient factors, such as shadows from nearby trees and so on. And we have shown that this kind of technique scales to a very large number of solar sites globally without requiring any new instrumentation. Now, the second project that I want to describe is called deep roof. Now, this technique uses computer vision to decide which rooftops of buildings or homes are good candidate for deploying solar arrays. And this is shown in the picture here, where you take a Google Map satellite view of a particular address that shows you the aerial view of that location. And then in that view, we can detect what is actually a building, what are nearby trees, and so on. And you do this using computer vision techniques. And then once you have determined which is the roof, we can actually do further analysis to extract the roof structure, the planes of the roof, what direction they face, and so on. And then you analyze that structure to figure out what planes are actually good candidates. So at the picture on the right, you see that there's one plane that is labeled green and one red that says that the south facing plane, which is green, is going to get maximum sunlight despite the presence of a tree nearby. You will still have highest production, and that would be a good candidate for installing solar arrays. Now, for a long time, this type of analysis has been done manually by having someone actually look at the site or at least look at the images. what we have done is automated this and built a system that allows us to do this for an entire city and all the buildings in the city. So you can quickly identify all the buildings and rooftops that are good candidates for solar installations. Now, the next project I want to talk about is called Watt Home. Now, here we are using machine learning techniques together with systems approaches to decide which buildings or homes are inefficient in terms of their energy usage. So the interesting thing here is we combine a physics model that are used by energy experts to model the energy usage of a building with machine learning techniques that allow us to deal with the stochastic nature of the energy usage. And the idea here is an older the building, the worse maybe its envelope or windows, and the higher its energy consumption. So what we do is we normalize the energy usage of homes by age, by size, and then use our machine learning technique to model the energy usage and its dependence on temperature. The more sensitive the energy usage to temperature, the less inefficient the building is going to be. And we find outliers in peer groups of buildings that are categorized by, say, age and size. And the idea is to find anomalies or anomalous usage patterns that tell us that something is wrong. And although it's not shown here in this slide, our machine learning techniques are also capable of classifying the types of problems that you might see, saying that maybe the air conditioner in the house is old, or the windows are old and they're leaking thermal energy and need to be replaced, or that the thermostat is misprogrammed and needs to be fixed. So we can not only find what kinds of anomalies exist, we can also find the cause of this anomalous behavior. Again, this type of technique is being designed in the context of city scale energy analysis, where we can analyze all the structures or buildings in a city, its energy usage, and find the worst offenders. The last project that I want to describe here is called vSolar. And here, what we are doing is using techniques that are well known in operating systems, networking, and distributed systems, and applying it in the energy context. So what we have done, as is shown in the figure on the right, is to build an energy virtualization layer where you can take physical assets such as solar array and and expose virtual solar arrays that you can then assign to a homeowner or maybe a owner within an apartment building where all the owners share a common physical array. So each homeowner gets an abstraction of a virtual array and a virtual battery that they own that they can use in any way they want, rather than depending on how the community as a whole uses the physical assets. So it exposes, in other words, independent control and multiplexes virtual resources onto physical resources, similar to how OS virtualization allows us to multiplex virtual computing resources onto physical resources. Now, interestingly, this kind of technique can be used to implement energy trading between owners, as well as allow you independent control of your share of a physical solar array's electric generation, or your share of how much energy is stored in a battery. So these four projects give a glimpse of our research that spans both AI techniques as well as systems techniques, and address interesting sustainability problems and allow us to design techniques that will put us on a path for a net zero future. So with that, I'm going to end the presentation. And I would like to point to two websites where you can find more information about our research as well as access to research papers. Thank you very much.